Hi, I'm Heinz Putz, and what we'll be doing today is learning to program a CNC mill, CNC machining center. Please state the time and write this number down. It's 614-888-8466. If you have any questions later, give me a call at this number, and I'll try to help you to the best of my ability. A CNC milling machine or a CNC machining center is capable of certain types of operations, and they're broken down into two groups. Basically, we can do drilling. Drilling is motion that is basically up and down. It would also include boring, it would include tapping, and besides that we can do milling with small cutters with large cutters. So we have two things that we can do. We can do a drilling type of operation, an up and down type of operation, or we can do a milling type of operation. And let's take a look at some of the typical parts made in machining centers. This part has a variety of operations. There was a turning operation to begin with, but all of the inside is actually contour milled out. It was not bored out. And there's a little recess. There are a number of holes. There are 1, 2, 3 to 4 tapped holes. It's an aluminum part, so it could be run quite fast. Here's a part requiring face milling, again drilling, tapping, a number of boring operations, and this part has 3 sides that are actually machined, so it would require fixturing on a vertical machining center, and possibly on a horizontal machining center it could be sitting on a turntable actually turning itself around, so we could work from 3 different or 4 different directions. This is a thread milling part, and the cutter you see is a thread milling cutter. To be able to do this, the machine would require a feature called helical interpolation. All of these parts were made on a vertical machining center. And let's take a look and see what a machine like that would look like. This would be a typical modern vertical machining center today. This is a machine very similar to the machine that made the actual parts you just saw. It's a 3-axis machining center with tool changer. It has a Fanuc 6M control. This particular machine has 16 tools that would be changed by specifying the proper tool number. This machine is also capable of doing thread milling. Thread milling would be the ability to do 3 motions at the same time. Now on this type of machine, sideways is always called the X direction, in and out is always called the Y direction, and up and down is always called the Z direction. The control has a screen that could be used as a readout, like right here. It's showing X0, Y0, and Z0, but it could also show the program that we're running. It could show a lot of different things, tool length offsets, coordinate system setting. And here is the X and the Y and the Z direction. And you notice something kind of interesting here. Take a look at the digits here. We have 3 digits behind the decimal point. That means that this particular machine is set up in metric. In inches, we would always be dealing with 4 digits. We're always dealing in tenths. Where in metric, we're always dealing with thousands of millimeters. Let's take a look at the tool changer on this type of machine. This is called the simplified tool changer. It does not have an arm to actually take the tool in and out of the spindle, and in programming, the pocket facing the spindle would always be empty, because when we asked for a new tool, the machine would always put the tool that's actually in the spindle into the facing pocket, rotate around to the tool we call for, and then exchange the tool. And what we have in the spindle right here is a face mill that could be used to face mill the part we saw a little earlier. We also have a number of drills here in our tool changer. We have a number of boring bars. We have a couple of taps, each of which requires for us to figure out the proper RPM, proper feed rate, of course the programming sequence to do that particular kind of operation. Hi, I'm Heinz Putz of the Center for CNC, and the first thing we'll do is we look at the coordinate system, but before we do that, let's look at our dimensions. The machine normally has 3 directions of travel. We have an X, we have a Y, and we have a Z direction. The numbers we'll be programming are given in tenths of thousands, so it will look like this. Now that's a typical inch setup. In metric, you would see a number that would look something like this. There are only 3 digits in metric. And the reason would be that metric is a much smaller unit than inches. So anytime you see a number like this, we're dealing with inches. And anytime you see this type of number on a machine, you're dealing in millimeters. Well, let's take a look at the coordinate system of the machine tool to begin with. And all of our numbers will be written to look something like this. We will use a decimal point to define the size of something. This would mean 1 inch. The control by itself will figure out the decimal points that go behind it. So we have to make sure that we place the decimal point properly. We cannot forget the decimal point. So our 3 directions of travel are X, Y, and Z, and we're dealing with 4-digit numbers. In and out motion, the machining center we just looked at a little while ago, side motion is X, and this motion would be called the Y direction. The numbers get bigger, that's called the positive direction. Numbers get smaller, that's called the negative direction. And in this direction, numbers get bigger the further we want to cut in that direction, they get smaller this way. Now, let's put a part into this coordinate system. Let's imagine we have a table of a machine. Here's the machine itself. Here's the table. We have a piece sitting here somewhere. What we try to do, we try to pick the most logical spot on this part to call it part 0. Somewhere on this part we would have the ability to say we want to start counting from this point, and it's usually this lower left hand corner. The reason would be that this is now positive and that this is positive. And if we start counting from here, that all our numbers would be in the positive direction and in the positive direction. So let's assume that on this particular part, this part is 4 inches long and this part is 2 inches high. Now, through coordinate system setting, which we'll do later, we will tell the machine that we want to start counting from here. Now, to define where these different points would be located, if we have a cutter that went around from here to here to here, down to here, finally across to here, that if this is 0, that would be called x0 and y0. This point up there would be called something in the y direction, and it would be the actual size of the part. If the part is 2, this is 2.0. This point right here would be located at x, and the actual part size is 4, that would be x4.0. This point down here would still be at x4.0, but in the y direction it would be at y0, because this represents y0 in this direction. And finally, this point is located at x0. So normally, if we have a square type of part, we pick the lower left-hand corner, because we can call that 0, 0 through coordinate system setting, and then we can actually program part dimensions. This point right here is y2.0. This point right here is x4.0, while it maintains the y2.0. This point down here is y0. And as I feed back in this direction, if I went back to back here, it would be x0 again. Most likely I would go to some point past that point. Now that's on a flat part. Now let's take a look at this coordinate system if we want to drill a couple of holes. Let's say we had a part that looked something like this right here. We have a drilled part. We want to count this right here to be 0, 0. And we'll do that later through a thing called coordinate system setting. Now we would like to drill a hole at 1 by 0.5 and another hole at 3 by 1.5. Now by the way, what you ought to do and what you ought to learn is lay out all dimensions on a part that they come from this point. From here to here is 1, and from here all the way over to here is 3. It's not from one hole to another. This layout, that all the dimensions come from this common point, where this dimension actually comes all the way from over here. This is called absolute programming. Absolute is a term that's represented later by a G code that will look something like this, G90, where all the dimensions come from a common point running this way and in this direction. But we'll get to that a little bit later on. So for now, all we want to do is we want to put the dimensions down for where these points are located within this coordinate system. This is 0, 0 on the part. So this would be located at x 1.0, the actual dimension of 1 inch, plus y 0.5. That is the location of this hole. This hole is located at x3. So this hole would be located at x3.0 and y 1.5. This dimension represents the distance from 0 to this hole in the x direction and in the y direction. And so does this. From here all the way to here is 3 inches. And from here all the way up to where the hole is located is 1.5. Now that's the normal way of programming today. Now let's take a look at an example where the dimensions cannot come from this point. Take a look at a part like this. Now, there is no square corner on this part. So what we normally do, this part would be partially turned in a lathe, and we have to indicate the center of this part, and all of our dimensions would come from the middle of this part. So we would be forced to be using plus and minus dimensions. And let's take a look at this and make up a little sequence of positions for this type of part. Let's assume that all of these holes are over 2.0 and up 2.0. This would be a part that has already been turned. The part is round, it has a bore. Now what we do is we come and we indicate this bore, and we pick this as the location from where we want to start counting. So that is 0, 0 for our purposes. Somewhere in our coordinate system would be the distance from the machine 0 to here. Normally the machine 0 is somewhere over here in this direction. So we would have the distance to here in the machine, plus we would have this distance in the machine. So the machine would know where this part is located through something called coordinate system setting, but we'll touch upon that later. For now though, the machine knows where this is located. Now how do we tell it where these holes are located? Now look at the coordinate system. This is positive, negative, positive, negative. We count from here. This hole is located at x 2.0 and y 2.0. This hole is still located at x 2.0. But now in the y direction, the hole goes over into the minus direction. So it would be y minus 2.0. This hole right here would be over in the x minus direction, minus 2.0, and also y minus 2.0. And this hole would be located in the x direction, minus something. It happens to be 2.0. In the x direction it's minus 2.0, but in the y direction it is positive 2.0. So sometimes you can't avoid it. You've got to have these positive negative signs in there. Actually there is no positive sign. Any number written is automatically positive, but you cannot avoid these negative signs. So positive, positive, positive by negative, 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 and this upper one is negative in one direction, positive in the other direction. Now, it is not really nearly as complicated as it looks, because what would happen if we drilled this hole and then we started drilling this hole, but we forget the minus sign right here? The control would think that we're asking it to drill another hole at the same location, and it would just drill this hole twice. So once you see this happen, where you forget a minus sign, it's very easy to remember where these signs are actually supposed to be. So to review it, the side travel is always called the x direction. The in and out travel on a vertical machine is always called the y direction. For us to move in that direction, our tool to move in that direction, the number gets bigger. To travel this way, the number gets smaller. Tool travels this way, the number gets bigger. Travel this way, the number gets smaller. Now that is the x and the y, and now let's take a look at the z direction. The up and down motion on this is always called the z direction. And the further we go away from a workpiece, let's assume this is a drill and this is a workpiece. So the further we go away from this, the bigger the numbers. And the closer we get, the smaller the numbers. Now, the way we set this up is that the top surface of this work part, let's assume this piece is maybe 1/2 inch thick, like that. The way we set this up through something called tool length compensation, where we bring this tool down and actually touch off here, and we put that information in the machine, we wind up telling the machine that this represents Z0. And that is done through a tool setting, through a tool length compensation. So, if we wanted to bring this tool down to a point where we're sitting 100 thousandths above this, let's say we want our tool to be in this position right here. And this distance right here is supposed to be 0.1. We would actually call that Z.1. Any number above this surface is a positive number, 1 inch, 2 inch, 3 inch, 4 inch, etc. And the closer we get to the surface, the smaller the numbers get. When we actually touch this surface right here, it's Z0. Now, let's assume we want to drill a hole right here. We want this hole to be about a 1/4 inch deep. If the numbers are positive above this work part, and if the numbers get smaller and smaller and smaller, then once we pass this, for us to achieve this depth right there, it would be something in our program that would look like this. It would read a G code, a G1 to Z minus something. Minus the actual number, 0.25. Anytime we see a number in our program that's a minus Z number, we have done something that passed the surface of this part. We have actually gone into our part. Anytime we see a number that's positive, we are clearing our work part, as long as we call the surface Z0. Now that's the coordinate system up and down on a machine like this. What you just saw in the coordinate system applies pretty much to every control in the world. X is always the side direction, Y is always in and out, and Z is always up and down. But let's just take a look at what our programming will pertain to. Programming the modern CNC control started basically back in 1980 with the Fanuc 6M control. This was approximately, and this came out was approximately 1980. 1980, 1981. The 6T control came out at the same time. Now, since then, there have been a whole number of controls. There have been a 10, 11. Right now, 0 and 15 are the controls that would be on most new machines. And what that would mean right now is that right now we're in 1992. Now, there have been a lot of control changes as far as control numbers. The inside has been worked on. It's been made more reliable. But the really nice thing about all this is that the programming method that was developed back in about 1980 for the 6M control has been changed very, very little. If you were to learn to program on a 6M control or on a 6T control, the only difference is that M means milling and T means turning. If you would have learned to program on one of these, there have been very, very minor changes all the way through. The same material that I can use to teach this control can be used to teach any of these other controls. The programming method is almost identical. Now, another really good point is, Fanuc is so strong in this field that most people will use this method of programming. So the same method can be used for the Yasna control. Very, very little change in the method of programming this or this. It can be used in the Fidel control. There's a new machine that's called Haas. They have their own control. Same method of programming. Mitsubishi control. And the same thing would apply to most lathes. If you learn to program on a 6T control, very minor changes you would be able to program on most other controls. So, What we'll be doing is we'll be looking at the Fanuc method of programming, basically any of these controls. Let's take a look at the typical coding for CNC mill programming. These are the letters we have to work with, and basically the letter O is a program number. This is called a program number. The number could be anything between 1 up to 9999. It could actually be more on the newer controls, and the only rule on this is you pick a number that's not already in the control. You number your program whatever you like, as long as you don't use the number that has already been put into the control. The end code is a block number. The typical way to do this would be to go N1 followed by N2 followed by N3, etc. There's a lot of freedom in this. You can program without block numbers.